Okay, welcome to this video. The kids are asleep. Um, New Year's is getting close, and it's time to do some live coding. So, what are we doing? Um, Today, I'm thinking that we'll write a task system with support for coroutines or asynchronous functions. Um, and let's see where that takes us. So every time I build systems of this nature, some of the details come out a bit differently. So um, um, let's try to build one and see what happens. So for the purpose of this video, I'm thinking uh, perhaps a couple of hours that I'll spend on it. So we will try to stick to the basics. Obviously, with a system like this, you can work on it for weeks, months, maybe even years, and keep tinkering and changing the different parts, optimizing it for various workloads and so forth. And there are a lot of details in the different corners of such a solution. So for the purpose of this video, we'll try to stick to just getting the core of that system in place and exploring some of the themes in there. The other thing I will say is that we will try to keep the control flow as transparent as possible, which means that there will be no weird control flow tricks to obfuscate what's going on, because with the way that a task scheduler works, it already introduces a lot of complexity in how the program is going to be executing. So we will not be adding more to that. So having said that sort of preface, let's get started with the code and see where it takes us. So a task system basically means that you have a number of workers dedicated to processing tasks that go into some sort of queue. And what's great about a system like that is that you can really control how you distribute the time slices dedicated to each task, when a task yields to other tasks. And you can also scale the system very easily from being completely single-threaded or using however number of threads is appropriate for the platform that you're running on. And things will sort of adapt to that automatically. With the coroutines, basically what that means is that we want functions that act like finite state machines. So you have a function that awaits another operation, and that operation might be an asynchronous operation, it might be an IO operation, or it might be several child tasks that are running computations. And you basically want to be able to express a sequence of operations that you want to run in sequence. However, there are steps within that operation that then branch out. Other things are happening. And then when all of that is completed, you want your chain to continue. And typically in languages that support this natively, there's like an await keyword. So you have asynchronous methods and there are await operations where you're basically awaiting some other method. So you can write your code as if it's as a sequential synchronized program, but in reality then at each of the await points, that function is actually broken up into different states that are then transitioned between. So we will implement such a state machine, although here we'll probably have that state machine explicitly laid out. So like a switch, a switch operation in the function that clearly you have to clearly specify each of those states, and then the function will re-enter transitioning into the different states. We'll see it when we start writing the code. That's something we want. And another thing that we'll try to squeeze in there is we basically want two different ways of running the asynchronous or invoking the asynchronous functions. So either we have a scenario where you're starting a new task in the task scheduler. So you basically start a new task, it gets queued, and at some point one of the workers is going to pick it up and start running the operation. And the operation has the task has an entry point, which is going to be one of these asynchronous functions. The other scenario we want to support is that you have a task that's already running, and within that asynchronous function, you want to call another asynchronous function and await the results and then continue executing. It would be possible to implement that using the entire task system. So you schedule a task at the end of the queue and await that. But for most purposes, it's very valuable if the system is able to start executing another asynchronous function directly. And if it turns out that the other asynchronous function actually completes synchronously, you don't even need to then schedule a task in the task system or involve any sort of yielding back to the scheduler, which is actually an important property for the system to have. So we'll try to also get that in there. So there's a lot we want to do, and let's see if 2 hours is enough or not. Okay, having said all of this, let's get started. So how do we start with something like this? So I think the best part is to start writing an asynchronous function the way that we imagine that it's going to work, and then let's work from there and see what needs to be implemented in order to support that intended API. So if we imagine that there is some async function here, and one of the key things here is that the way that we'll have to implement these coroutines means that there is no stack that's preserved between the state changes. So these are sometimes called stackless coroutines. That is simply because since we're not doing any weird control flow shenanigans, we will have to return from this function whenever there's an await point or we're doing a straight state transition. So everything on the stack will be lost at that point, and when we re-enter the function in a different state, there's a fresh stack for us. So that means that all of the state that's persisted between the state changes needs to go into some state structure that we pass in as a data pointer, basically. So that's one aspect. The other part, so that structure will be custom for each asynchronous function. So each asynchronous function will have its own structure with whatever data is necessary for that one to hold. The other thing that needs to get passed in is some sort of context structure, which represents the work or the task that is currently being executed. So in that structure, we will have things such as the current finite state machine state. Which state are we in? We might have some memory arena in there to do allocations for the temporary allocations for the task, and any other information that's generally required in order to execute any async function. So we can imagine that there's some sort of task structure, and maybe the task structure has some finite state machine state. So this one is getting passed in. Now, I mentioned before that we want to be able to support calling other asynchronous functions directly. And when we call them, we want the task to sort of move. We're almost pushing another async state onto some sort of virtual stack where we are executing this first function. So if we imagine some sort of pseudocode, we have bar over here, that's some sort of async function, and then foo is here. And here we might say await boo, and then some other stuff happens. When we enter, bar. When we enter bar, bar might call some other operations. We might do some IO op. So bar also has multiple states, right? So here is state 0, and then this one happens, and here state 1 resumes, and then finally the function ends. So here we have state 0. When the await operation completes, we return to the function. Now we are in state 1. When we enter bar, we need to track the state machine state of our invocation of the asynchronous function bar, while still remembering where we were in foo. And this might, be nested even further. So actually, there needs to be some sort of stack here, where whenever we do another async operation call, we push onto that stack so that we can then pop it when the function completes, and we continue off, where we were in the previous level. So this finite state machine state actually needs to go in some other structure. So let's call it async context. And let's put it over here. And then in task, we might have a number of these. Okay. Let me move this one down here. So I'm just putting an arbitrary number here. We can figure out what that needs to be later on, but at the moment we have a fixed allowed depth of 16 calls. And then maybe we need a number to track where the top of the stack is. So if we go back here, we can then assume that, okay, we need the task because this one might have other stuff in it, like a memory arena or something. And then we have this async context, which for now contains this finite state machine state. But we'll need more stuff in here. For instance, the result of it in wait, or tracking somehow the fact that we are awaiting something, so that the task scheduler knows when to get back to us. So the structure of an async function then might look something like this, where we have a switch, and then we have the various states of the function. So a purely synchronous function would have only state 0, stuff happens, and then the task completes. If we do some sort of await operation on something here in case 0, we then specify which state to return to when the operation is completed, which could then be state number 1 in this case. So we will define these states by hand, manually. Obviously, if we had some sort of pre-compiler, pre-processing mechanism running, we could take code that looks like this and generate this state machine. But we're not going to do that in this video. We'll keep things simple so that we have also clarity and transparency into what's actually going on. So let's now look at this. We have our various states, and this function needs to be able to return something that informs the task scheduler, which we haven't written yet, what the state of the asynchronous function is. So there are 3 possible things that could happen. Actually, maybe even 4 or 5, but let's start counting them. So either the function has completed successfully, or the function had an error. Now, we could either separate the 2 states, so successful completion and completed with an error, as 2 different return states, or the error could be handled differently. But let's for now assume that error is a return condition, a first-class return condition, return state. The third thing that could happen is that we are awaiting something. Now, we could be awaiting different types of things, and we'll see if it's possible to consolidate those things, or if they will all be different types of return result values. So we could, for instance, if we start another task, we could await the completion of that task. Or if we're just invoking or calling another asynchronous function, we could be awaiting the completion of that one. And these 2 things are probably going to be technically different in the implementation and might require different types of return data for the task scheduler to know what to do. There's also another scenario where we just yield our time slice, and that's useful if you're using these as coroutines, or so we're not perhaps doing any asynchronous operations, but we just want to have control over when the scheduler switches from one task to the next, if the tasks are very long running. And this can be very useful, as opposed to, let's say, if you just spawn a bunch of threads and have the kernel do that for you. So the downside of letting the kernel do that is that the kernel does not know how to prioritize the different things that you've spawned. If you spawn 10,000 different threads, it will switch context between these like crazy, trying to treat each of them fairly, unless they have different priorities and so forth. And doing that will trash the performance of your system, because each of these context switches is actually pretty expensive. So if you know that I'd like to I would want the task to be computed in a different way, or prioritized differently, or if there are good points in time where it's appropriate for a task to yield, then this method allows you that sort of fine-grained control. So a yield operation is something that a coroutine should also be able to do, where you just allow another task to run. Then it will come back to you once it's your turn again. So we would also have that. Then depending on how complex you want the system, you could potentially also have built-in support for a time delay. Come back in a few milliseconds, and you specify the time as part of something that's supported in the scheduler. So either way, it means that the function needs to return something. Now, this something can either be an enum, or it could be a struct. Now, let's start with an enum. And if there's data associated with the result, we'll put it in the task structure or in the async context. And then let's see if the decision holds all the way. So if we create an enum, let's simplify the name. We have the OK, we have error, we have yield, and we have await. And then we'll decide if await needs to be specified further. Now, a bunch of these need additional information, so let's create functions that we can call to take additional parameters that we'll then store in the task or async context as structs. So, for instance, if we do a async OK, in this case, we might not need any further information, but oh yeah, maybe I'll say go to. Whilst if we have an async error, there might be an error message of some sort, and that error message needs to be stored somewhere. So for now, let's just assume that we'll do something like this, and then we'll decide later exactly how to do that, and where to store it and so forth. Then we have perhaps the most interesting part. Well, the weight is the most interesting part, but let's look at the yield. So in the case where we are yielding the task, we want to know, we want to know where you intend to return afterwards. So that's the yield, and that will also be true for goTo. The question is now, do we really need goTo? Yield would basically just be returned to the same state that could be implemented as the goTo. Do we really need yield? Let me think about that. It might just be a convenient thing to be able to do so that you don't have to pass in the current. Let's do it like this for now. It might be superfluous to have the yield function, but let's keep it for now. So that's the goTo, and then we have the wait. Which, as we said before, might be two different, might actually turn out to be two different types of return values depending on what you're awaiting. So let us now look at what we've got. So this mostly boilerplate. So here we would then do async. Let's do our example that we had below. Bar async. So here we want to await bar. But before we get to that, because we haven't implemented how that should work yet. So here we just do the async OK. We'll have a default case which should just panic. I'm using my panic macro here. That's the only thing I've pulled in from my previous code base. Everything else we're writing from scratch, but some things are just so convenient to have. Unexpected FSM state. Oh, sorry, async. Okay, so here we now need to figure out what does the syntax for await actually look like. So actually, let's call this one. Oh, okay, is good. Okay. Okay, so how does this get invoked? we also haven't specified our state variable yet. So let's start looking at how we imagine this whole thing going down, right? So we have to have some sort of process async function, and we have our task. We have this stack of async contexts, and we know where the top of the stack is. Basically, what we want to happen here is that we call process async on the task. It gives us a return value. So let's pretend like we have a task here. We'll call process async. It will give us some results. We will look at that result. We'll do something based on what the result says. And then if this task is still active at some later point, we will again call process async on the same task. And it will do the next step in whatever needs to happen in the execution of the asynchronous function. So one of the things that then becomes obvious is that the async context here needs to have a function pointer to the asynchronous function. And probably that function pointer will look something like let's do the type def later. We can just call it yeah, we need the data variable as well. So we have enum async result. You go up there. Process. We have the task. We have the async context. And then we have the void pointer with the data. I have to declare that. And here it's just complaining about the padding. This is also a complaint about padding. So in process async, we will get the top context, and then we will execute it. Or process it. And here, the data needs to be stored on the async context. We pass in the data. Async result. We look at the async result. Let me get all of this. Okay. So different things will happen in the different scenarios here. So if we are done, then we need to pop the async context, unless we are at the top, in which case the operation is completed. So in this case, the fact that OK and error are separate things is less interesting. Let's start like that, and then we'll see how we want to do it. So in both of these cases, the asynchronous function has completed. Now, if we are at the top of the stack, then we are done. If we are not at the top of the stack, we want to pop that stack, and then we basically want to run again. We also need to then provide the result of the asynchronous operation. So let's see now. The results should be stored somewhere in the async context. So that when we come back, so if we look at the foo operation here, when we return to foo from having executed bar, and we enter the state machine state 1, we need to be able to inspect the result of running bar. So let's say bar generated an error. We need to be able to see that here. So the result of calling bar needs to be stored somewhere. Now, there are a number of options where we actually store that. So either we let it remain in the async context, that belong to bar. So when we pop that stack, you can still reference the old async context of bar to see what the result was. The downside of that is that if we later are awaiting other types of things, so let's say that we later add the ability to spawn new tasks and await their completion, those are separate tasks that will run in the scheduler. So later on, if we get there, we can do an operation which spawns multiple child tasks and then collects the results of all of those operations and then continues on and does something else. So it's a pretty good use case for this type of system. In a scenario like that, there is no async context of the call, right? Because that's running on a completely different task, And so the results of that operation needs to be stored somewhere else somehow. So I'm thinking that probably when you await something, that should create the async context that did the await operation should probably be the one to store the results of that operation. So you should go to this one at the call site. Maybe it passes some information or pointer along to something so that the target process knows where to store the results or something of that nature. So if we work on that idea, then what it means is that when this operation completes, either the async context here has been informed of where to store the result, or it stores its own result in its own async context, and here we have to copy it to the parent async context into some sort of await result structure. So I'm actually uncertain of this. So let's get back to the problem. But basically, we will get back to the problem. But for now, we can say that if we're not at the top of the stack, we pop the stack one level, and then we return a yield because we want to continue executing now that we're back at the top level. Now, it would also be possible here to add another async result, which is just again a repeat or something of that nature. So we don't want to yield the time slice. We would like to be invoked instantly again. So I think in all of these cases, we just return the result. This is the only scenario where something needs to happen. So if we're at the top, we go down and then we say again. If we're at the top of the stack, then we're just done, right? Then whatever the result was is the result, and nothing else is going to happen. I'll put a break there, but really we're returning on all the states. And let's also put this one here. And new panic. This obviously should not happen, but just in case, we'd like to crash. Okay. So now we need to do that await operation properly. Also, these functions need the data pointer. So how does the await actually work? It's not going to work like this. It's a lot more complicated. So we basically need to specify the next, let's put this in. We need the function pointer to the next function, to the next asynchronous function. So if we do a wait, what did I do? Oh yeah. What did I do wrong? It's not how you oh yeah. Stupid. Yes. Obviously async func. So here we have an async func. And here we want an async func. And basically two things need to happen. We need to store on our current state. So well, I'm passing it in, but let's say current is this one, sorry. And then we're popping, or we're pushing a new state onto that. So next state is or I can do this instead. And we want to make sure that where's that? Let's do oh yeah, so let's make sure that we are Oh, yeah. Well, it needs to be, there we go. +1 still needs to be less than the maximum depth. We get the current one, and then we increase the top pointer or top position. So we push a new one in, and then we get this one. Okay, I don't have that. Well, I'd like to zero that one. Let me just do quickly. Let me just check this so I don't get it wrong. We have A. Want to write zeros. Size of A. It's defined in string. Okay, zero that struct, and then we want to say that the function is this one. The data, I also have the pass. And FSM state will be 0. And that's it, really. And then we say, so that's what needs to go into the next async context. So now it knows what's the function pointer, what's the data. We start always at the finite state machine state 0. That's where we enter the function. Now, the interesting question is, what do we put on our current async context? Because this one, here we need to somehow track the fact that we are awaiting the completion of some operation, because that will trigger that will determine when it's appropriate to resume it. Now, in this particular case, it's not going to matter because in the code we wrote here, we just assume what's going to happen. But later on, if we're awaiting other tasks and so forth, it will become relevant. So the question is now, do we have enough to try this out? So there's the async. I don't actually need to pass this in. Oh yeah, the next FSM state. This one needs to be stored because we want to know when we come back, which state are we returning to? The thing is, we can probably just go ahead and set it, right? The only risk with this is that if you abuse the system here and you call async await, but you don't return, and then you keep doing other things, and then you inspect the FSM state variable, you might run into a weird state. But at that point, you've basically violated the API, and it's C, so there are a ton of footguns here. As long as one follows the intended way of writing the code, which is that you always return from the function. If you call any of these, then it should be fine. So for now, let's not worry about that. So we pass in this bar function. That's the one we want to call. We don't have a data pointer at the moment for any of these, so just pass in 0, and then the next state is 1. And then the function completes. In here, nothing really happens. So now, oh yeah, a bunch of unused parameter errors. Let me just get rid of these warnings so that we can see if there's anything we need to actually care about. So there we go. Got this one. We've got that one. And we have this one. Right, so we have our task, and I'm going to just initialize it. Set this to foo. And then here, basically we say, so if we get either of these two, we'll exit the program. Otherwise, we'll just keep going. And now, this is not correct, but I just want to run. I want to reach something we can run so that we can see what's going on. So here, let's do a printf. Actually, we can do like this: foo async, and then which state are we in, and bar async. Oh, sorry. Get rid of these. Okay, so we enter foo async in state 0, then we jump to bar async in state 0, Then we come back to foo async in state 1. So far, it's doing what we intended it to do. Now, I'm going to let us step through the code. Okay, so we've got this. We enter the process async function. We get the async context at the top. We call it. We go into await. We add a new async context. You can see it there. We zero that struct. We set the process function to bar async. We set the data pointer, which is just a null at this point. And then we update the next FSM state of the current async context, which is the one that's executing the foo async function. And then we return the await operation. So here, it's going to say again. So we come here and then we run again. We get the top async context, which now is the one that's going to call bar. We call it, we enter bar, and then it returns an OK. We are not at the top of the stack, so we pop one level, and then we say run async again. So we come in here, we run it again. Now we're back at the state that runs foo. The finite state machine state has been updated to 1. We enter the function foo. Now we jump to state 1 and the method completes. We pop. Well, we attempt to pop. We realize that we're at the top of the stack. So the entire async chain has completed. So we return the value and we're done. Okay, very good. So far we have some basic stuff going on. Now, now let's see how we can propagate results back to the parent function. Or we can flesh out the actual scheduler a bit more so that there's something exciting going on here. Maybe look at what awaiting the child tasks would look like, because given the constraints of this particular video, doing an actual asynchronous I/O thing would require introducing either a network connection or something like that, and suddenly the whole system gets a lot more complicated, and I want to keep it contained so that it's easy to follow along with everything that's happening. So we might do another video. Last time I said that, it took like 5 years before I did another video, but hopefully I'll be able to do another video in the not too distant future, and we can try to do an actual async IO thing with a network connection or something of that nature. But what we can do now is to do the thing I mentioned before, where you might have a task that then spawns a number of child tasks. So we could have some computation that we want to parallelize. So each child task gets a portion of the computation to perform. And then when all of the children have completed, um, we want to return control to the main task and then continue with additional steps. So we have the scenario again that I mentioned in the beginning, where you have a sequential chain of things that need to happen, but each of the steps in the chain might involve, lots of parallel stuff going on, or non-synchronous operations. So in this case, if our scheduler has multiple threads running, when we spawn those child tasks, they can get picked up by how many ever workers are available, and those will run them in parallel. So if we want to do something like that, then it's now important to get the actual scheduler a bit more fleshed out, and there needs to be some sort of queue for the scheduler to work on. So the queue needs to contain various requests to either start new tasks or to resume tasks. So one way to do this would be that if we have child tasks, then whenever a child task completes, it will wake the parent up for the parent to then determine if it needs to act on that event. At least that's one way of doing it. So it will sort of depend on what you've awaited. So there are so many different ways to do this. We could either support awaiting on individual child tasks, await all children's completion of all the child tasks, or have it wake up after each. There are a number of options there, but let's start writing the code, and then we can sort of decide along the way. So first of all, we're going to need another sort of structure here. I'm going to call it world. It's just going to represent the state of our entire application. So in the world state, we will have this queue. And we will also need to have a list of the tasks. Now, we could also reference the tasks by pointer. I usually like to avoid pointers and have IDs so that you don't keep a bunch of pointers in different places. But I also don't want to implement a hash map right now. So the question is, do we just ignore the performance implications of the task lookup, do some simple brute force thing, or do we store the pointers to the task? So the reason we'll need to be able to reference a task somehow is if we want to awaken a task that's pending or waiting on the completion of something else, there needs to be some way to reference that task. So one way could be if the tasks have IDs that are unique, one way would be to just use that ID. But then, you need to be able to somehow find the task based on the ID, and that's the part where we could do some simple thing. I'm not sure if that's a good idea, because typically you'd have maybe a hash map or something to quickly look up, to do a lookup. So let me just think about this a few seconds. Let's get back to that problem shortly, but for now, we can create the entries that go into the queue. And we can call those let's see. Let's call it just request for now. It's not a good name, but let's go with that so that we don't waste too much time coming up with names. We'll give the queue a max size. And we will have a read position and a write position. So we'll use this as a circular buffer. We have two cursors. One is the position at which we'll write, and the other is where we read. And the requests themselves will contain basically let's do request type. So either spawn a task or resume it. And if we are spawning a task, then we need to know what the function is. That's the entry point, or let's call it entry point, and the associated data. And then if we are resuming a task, let's call it, and then this one can be just resume request. So that one goes there. Have to pad again. So if we are resuming the task, here's the part that I mentioned before. So how do we reference the task? So to keep things simple, it could be that we need to have a pointer to the task in order to do that. What I don't like about this is that this is sort of, this represents the work of the task. So that's the state of the task as it's executing. It is not really an appropriate handle for some other task or other parts of the system to use or even know about. So that's why I don't really like doing it like this. So we might change this again, but let's just move forward. So we have this thing with the requests, and here we also probably need to keep well, we may or may not need to keep a list of the tasks. There's another thing here in spawn, and this is a similar problem where, well, this is very similar to this one. So either you have access to the parent or you don't, and we'll have to see which one we actually do. And here, then you would have your parent task if there is one. If there is one. Okay, so we're starting to get somewhere. Now we need to be able to enqueue in this. Question is now, do we want to introduce mutex as, or do we want to do some sort of lock-free queue? Again, I don't want to waste too much time on that because it's not really the point of the video. Let's do a stupid lock-free solution, just to not introduce mutex as. I'll do something like this. I'll explain what it is I'm going to do. So when we enqueue, we have this world state, and I have a request. Then I will do so this is a, don't do this, by the way, but we'll just do that now. So basically I'm using this variable as a poor man's mutex. So I'm saying that I'm doing a compare and set operation, where basically I expect the value to be 0 and I want to set it to 1. If it's not 0, if it's already locked, if it's already 1, this operation fails and E will contain the actual value, which I know is 1. So then I set expected value back to 0 again and retry the operation until I enter this section, and I'll know that no one else is in there at the same time. And at the end, I'll just write a 0 back to the log. So again, don't do this at home, but we'll just do it because I don't want to introduce mutexes and do all of that. So we'll do this to keep things very simple. So now I will look at the right position, and the right position needs to be ahead of the read position. And they also, it's a circular queue, so they will circle sort of around the queue. So I can use the values of read and write, which will increase forever, to see whether there is anything for me to read. So I can do this. Or I can just check that the write position is greater than the read position. I can also check that the write has not completed a full lap and return back to where the read position is. So before we do all the checks, just to make sure we do things correctly, I'll think through the checks one more time. But if everything is good, basically we do this, 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 and we copy it into this position. And then we return. Then result is true, which will return. In the other scenario, then the queue is full, and we won't be able to write anything. So here we'll basically say the length of the queue is the write position minus the read position. And if the length of the queue do that. Otherwise, we fail to write because the queue is full. And then we can do a dequeue request. We will copy it out to that variable. Again, we lock, then unlock, return result. That's the result. In here, if read position less than write position, that's all we need to know, then the result is true. And then we basically say request out is world requests world read plus plus. Oh, mapped back onto the range. There we go. So we dequeued that request. Now, here, so the thing that's, we won't worry about it at the moment, is that later on, maybe you want the threads to sleep when there's no work to do, and then have some sort of event that triggers them when there are items in the queue. But again, all of that requires introducing, condition variables, semaphores, and stuff like that. And to keep things very simple, we'll probably just do a lazy polling of that, and then you get the gist of the idea. And then later on, maybe I can cover different techniques to not have your threads just lazily looping around and polling when there's nothing going on. For a scenario where the system is under heavy load, it's not going to matter, but it will matter if requests are coming in very sporadically, which wouldn't be uncommon for a server application. Okay, so now we can introduce a function which basically says pop and process request from the world. So we'll have dequeue request. If we don't, we return. Otherwise, there is some work to do. Let's look at the request type. Well, we do nothing. We want to spawn. We want to resume. This can't be const if we want to do it like that. Okay. Neither can this if we want to implement it like this. Never mind. There are ways to do it differently if the const correctness is important, but then again we'd have to have those IDs or references and an ability to do a lookup and get the actual task state. Okay. Anyway, so here we are. We may or may not have a task to process. If we have a task to process, then this is basically what we're doing. We'll run the task. Oh, we got 2 R's now. So this is why you should use the short names for stuff. Also, what's great about working in pure C is that there is no naming conflict between types and other things, which I personally like because I want the struct to be called task and the variable to be called task, and there's no problem in C. Okay, so we process a task. Here we could actually do something like while this is equal to again. We'll just keep going. And then finally we exit, and I need to think now. If you yield, go to is actually not, that doesn't make any sense. That one needs to go. Because if I'm doing a go to, that is just changing the next FSM state. But then I'm basically doing an again. Right? There is like no task, async, task, top. Right? Because from the outside world, from the perspective of the scheduler, there's nothing for me to do differently. That information is not useful. All I need to know is, are you yielding your time slice, or do you want to go again? If you're yielding your time slice, then let me go down here. If you're yielding your time slice, then I can reschedule you for processing. Right? So here I can say wait. So if you're awaiting something, you want to come back at some point. If you're just yielding control, then in queue, so let's see if this makes sense. I'm just going to do that. I'll put you at the back of the queue to come back. If there's no task. This is mostly just in case there's some corrupt data in the system, because this is not supposed to happen. Okay, so I put you at the back of the queue and then we're done. If the task is completed, we need to clean it up. So here's the part where using the IDs is actually really good, because if for some reason the relationship between things gets messed up, you might run into a situation where you clean up the task and then someone else has a reference to the task, even though it's completed. You'd never run into that problem if they have an ID, and then if they attempt to access a task or resume it or whatever, the system will detect that the task no longer exists and will handle that gracefully, rather than what might happen otherwise. So I probably would have preferred to do a solution like that. And we might still do it, even though the lookup is going to be subpar, just to demonstrate the idea of what the API should look like. Anyway, if we now go back to this, so if we're spawning task is begin task, if we are resuming, then task is for now, and then actually to prepare for what might happen later, we should do this. We might put it in the world state later. So here, resume task. World request resume. And here nothing happens. Okay. It just creates a new task here. So here now we need to allocate the task. We also want to maybe later have a memory arena for the task to hold its memory. Now we could have a bunch of these task structures lying around and use them from a pool. But let's start with a silly solution to just malloc the struct. process function, we have the entry point. I don't love this at all, actually. In fact, I kind of hate it, but it's the fastest way to get forward. So, but basically, just to explain here, we'll be spawning a bunch of tasks in a real scenario. We don't want to be mallocing and freeing these things. So we'd like to have a pool of these task structs, or just have we'd basically want that so that first of all, the same memory is reused when we're doing a lot of tasks quickly, one after the other. Second of all, to not be doing a lot of allocations and freeing memory during the execution of the system, because in reality you will have a actual maximum number of concurrent tasks that will happen depending on the characteristics of your particular program. And ideally, once the system, either you know it very well so you can pre-allocate those tasks, or your system will adaptively reach that threshold, and then that memory is just there and available, and you don't constantly you're not constantly acquiring and releasing memory. So we don't want it really to work like this, but it gets us moving forward very quickly. So we'll get back to that part later. So here, basically in this scenario, we end the task. But before we end the task, certain things need to happen, right? So if we, for instance, if we have a parent task, we may need to resume it. The other thing that we need to handle here is that a task should never be concurrently executed. So when resuming a task here, if the task is already running, we should not resume it again. So we can either prevent the resume from getting enqueued, or if we enter here and we see that the task is active, then we might re-enqueue the resume of the task. Now this is one of those parts that I mentioned in the beginning, that you can do a lot of work on this and optimizing this for various behaviors. We can't spend all that time on each little detail, but we need to make sure that the system is robust. And in order to do that, we have to ensure that we never execute one task concurrently from different threads, because that's the assumption here, is that a particular task only runs in one thread at a time, although it might switch threads. So every time it resumes might be a different thread that picks it up, but it should never execute from multiple threads at the same time. So we need to handle this somehow, but it won't be the ideal way. So what we could do here is resume task result. Okay. Either it's okay, or try again. Oh yeah. So we have the pointers in this case. We will never, but you know, if we want to switch it up, this could happen. Let's see. I only really care about the just enqueue it back. And then basically we can do okay. Let's do something like this for now. So we go to task. We add a that thing. We add a flag that says where the task is active. When we suspend the task, which we'll get back to, we'll set it to false. When we begin the task, it will be set to 1. And when we resume, we will attempt let's also do this right now. the expected value is 0. So in this case, it's already active. So we say try again. So again, we're doing the compare exchange. We expect the value to be 0. We want to set it to 1. If we fail, means that it wasn't 0. So then we do the again operation. This scenario is just a stub at the moment, but if we change this to be an ID, then this could happen. And then in this case, we've set active to 1. We're setting the out pointer and we're good to go. Actually, I have to set this to 0. Because we dropped down here. So now it is important to here either suspend or end the task. So in all the other cases, now if the task has a parent, now is a good time to do something about the parent. So I think we need to explain why we're resuming the parent. So in the resume request, I think that the parent needs to know the reason for the resume. So let's decide what happens there in a moment. So this should theoretically work for, if we do a spawn is type spawn to spawn a task, and the entry point is what else do we have there? That's it. The entry point is full async. There's no data. If I now say enqueue request, I put a moral state on the stack. And then we do while pop and process request. That should work, but it doesn't. So async await bar. Right, so here it says await, but this type of await, this one actually should return again. Now it works again, okay. So let us also try yield. So we create a function that's going to count. And now we'll need our data pointer. So let's imagine we have a counter. Within this function, we will do the following. While let me think of something good. Okay. Now that I think of it, we also need the way to just await and then end. So basically, provide a next FSM state value that indicates that we don't want to return here whatever is the return value from the other async function. We just want to pass that along. So here, if the counter reaches 1,000,000, we return. Otherwise, we're counting up to 100, and for each of the numbers, then basically we can do It's not a great example. I wanted to do a yield. I need to have some sort of, I need a more expensive operation because this operation is too cheap to actually matter. It's too cheap to actually matter. So let's see if we go to this one. We can do the following. I was just going to count a bunch of times. Then, oh yeah, let's do this. Okay, so that's going to be super slow. Let me shorten the duration of that. Oh yeah, I can't keep doing that. All right, I only want to do that whilst. See if I can create a test scenario that actually makes sense. Well, I mean, this one kind of makes sense. So I enter the counter one. I count to 100, and then I yield, and then this other task runs. And when that one completes, my count function gets another time slice, does the next 100, and then there are no other competing tasks, and it runs to the end. So we sort of have the basics of that working. Now we could try having another thread running at the same time to see how that affects things. Or we could try to complete this thing with a pattern, with a parent and do wait. So unfortunately, the 2 hours have run out. I wanted to get a little further than we did, but I think we did pretty well still. The only thing I hope that, I was hoping that we'd also have the time to do is these child tasks so that we can run an actual operation that then spawns a bunch of child tasks and then waits them and so forth. But what I think we'll do is that I'll follow this up with another video and we'll complete that part. So let's leave it at this state for this video, and wrap it up in the next one. And then maybe, you know, we have another 2 hours. It's possible to do a bunch of more fancy features that we talked about, but we're going to skip. Okay, so thank you for watching so far, and I'll see you all next time.